Hello, everyone. My name is Jon R, and I'm a professor at the Harvard Graduate School of Education. I'm pleased to be spending a little time talking with you today about mathematical flexibility. I'm sorry that I am not able to give this presentation synchronously or live. In addition to my teaching and research responsibilities at Harvard University, I also teach mathematics to middle school and high school students each morning. So as you are viewing this recording, I will be teaching a very lively group of grade 8 students. But I have included my email address on this slide, and I would be happy to respond via email to any questions that you have about my remarks. In this brief talk, I would like to introduce you to the idea of mathematical flexibility and advocate for its importance as a learning outcome, particularly in middle and secondary school mathematics. In this talk, I hope to answer the following three questions. First, what is mathematical flexibility? Second, why is mathematical flexibility an important learning outcome for students, especially at the secondary level? And three, what teaching practices help promote flexibility? Let me begin by defining what I mean by mathematical flexibility, and I will do so by looking at a few examples that I find to be illustrative. Let's begin with this problem, which is a problem commonly taught in the algebra curriculum, a simple linear equation. In many countries around the world, there is an algorithm taught for how to solve this problem that looks like this. But there are actually many other ways that this problem can be solved. I highlight this method. I point your attention to the fact that the last step of the method on the left involves dividing both sides by 3. We can divide both sides by 3 as the first step in an alternative method. That leads us to a solution in arguably a better way. However, note that if I change the problem slightly and change the 15 to a 14, both of these strategies still work. Here is the more standard approach, and here is the alternative approach. And you can see the divide to both sides step highlighted. But I might argue that in this second problem, perhaps in the minds of students, the first method might be better because it avoids having to add or subtract fractions, which students find challenging or which often lead to error. Now, you might not agree with me in my claim here about which strategy is better for either of these problems. But what I hope that I am starting to illustrate is that there are many ways that this algebra problem can be solved, and that we might have a conversation, perhaps even an argument, about which ways might be best under certain conditions. Here is another example. Again, a linear equation to solve in algebra. Here is a standard way that this problem is solved. We note in this standard way that one of the steps is where I combine the 4x and the 3x to give 7x. This process of combining like terms is something that I can actually do in a first step in the solution on the right side of the slide, yielding 7 quantity x plus 2 equals 21. And then you'll remember this divide to both sides step here on the left. I can divide to both sides here as my next step, producing a solution which I would argue is better. This is not a standard algorithm, but this is a particularly innovative strategy that can be used on this problem. Note that with this example, this better strategy only works because of the particular structural mathematical features of this problem, namely the repeated x plus 2 terms. If one of these x plus 2 terms were changed to x plus 1, the better strategy on the right side of the slide would no longer be applicable, but the standard strategy on the left would. As I will talk about in a moment, I believe that flexibility is particularly important in secondary mathematics, but I believe it is useful generally. And let me show you two additional examples from arithmetic that make that point. Here is a fraction addition problem, and I'm going to show you several ways that this problem could be solved. First, I show you a method I call method B, which is that we obtain a common denominator for the four fractions and then add them together. Here is a method that I call method A, which is very similar to method B, except the common denominator here is 27, which a student might obtain by multiplying 3 times 9. And then a third method, which I call method C, is to recognize that if you switch the order of the second and the third terms, then you would end up with two very easy to add fractions that make the problem much simpler to do. As before, this example illustrates that it might be challenging to determine objectively which of these strategies is better, and that you may or may not agree with me about which of these three strategies is the best. For example, is a common denominator of 27, is that a worse way to solve this problem? This question is certainly nuanced. But I would also say that the discipline of mathematics might argue that the answer to the question of whether any strategy is objectively better than another might be yes. It isn't essential to my argument, I repeat, that you agree with my characterization of which strategy here might be best. Rather, I hope you can see that there are multiple ways to solve any math problem, and that we can have a conversation about which ways might be better or more elegant, or more appropriate in certain situations than others. Engaging in the conversation about the relative merits of particular strategies is a deeply mathematical and important conversation, a conversation that's an important part of what it means to know and do mathematics, and a conversation that our students, especially at the secondary level, should be engaged in. One final example. Here is an arithmetic problem. And again, let me show you several ways that this problem could be approached. A very standard way might be just to operate from left to right, adding or subtracting numbers as one goes. But perhaps you notice that there are other ways. For example, if I switch the order of the second and the third terms, then I end up with very easy to add or subtract pairs of numbers. And this looks like it might be an easier way to do this problem. But here's a third way where I could again notice that if I switch these two terms, things might get easier. But then maybe I decide to only do the first two terms, but then move from left to right. Is this way worse than method B? Better than method B? Again, we could have a conversation about this. So as these examples are trying to illustrate, flexibility is something that I believe to be very important, and it's time now for me to explicitly define what I mean by that. When we think of the word flexibility just in the English language and not connected with any mathematical meaning, then flexibility might be related to responsiveness to changing conditions, the ability to adapt to new circumstances, a willingness to modify one's approach when necessary, an avoidance of rigidity, and a lack of persistence with ineffective or inefficient approaches. Thinking about what that means in a problem-solving context, flexibility would mean the willingness to modify one's problem-solving strategies when faced with challenging problems or problem-solving difficulties or failure, a willingness to change strategies based on a particular problem, the conditions for that problem, and the problem-solving goals. And these goals could include efficiency, wanting to produce a solution that's as efficient as possible, but could also include avoidance of errors, rigor, elegance, ease, and perhaps other goals. So, more formally, what I call mathematical flexibility can be thought of as having the following two features. While attending to the structural features of a problem, a student who is flexible considers which strategies could be used and which strategies should be used for the problem, considering one's problem-solving goals. And the student is able to implement the most appropriate strategy for that problem. Elsewhere, I have labeled these two features of flexibility as first, knowledge of multiple strategies, and second, the ability to select the most appropriate strategy for a given problem. With this definition of flexibility, let's turn to the question of why I think flexibility is important. Although there are relatively few studies on flexibility, we see emerging signs that flexibility is linked to improved mathematical performance. Students who are flexible are able to solve more problems correctly. Students who are taking more advanced coursework are more flexible than those who are not. Students in high-achieving countries are generally more flexible than students in low-achieving countries. And students who are flexible also have greater conceptual understanding of the mathematics. In addition, flexibility also has inherent disciplinary value. I alluded to this earlier when I was talking about some of the examples, but doing mathematics is much more than the ability to generate correct answers to a problem. In mathematics, we also care about how one solves a problem. The discipline places great value on innovative, clever, optimal, elegant, and/or efficient methods of solving problems and of doing proofs. By pushing our students to become flexible and by engaging them in conversations about multiple methods and which methods are best for a given problem or situation, we're giving students an opportunity to participate in a practice that is core to what mathematics is all about. In addition, flexibility may be especially important in secondary mathematics. As students transition out of arithmetic and into the symbols and abstraction of algebra, we hope that they become comfortable with the use of symbolic language of mathematics. As they move into the algebra curriculum, the symbolic procedures that they learn and use become quite complex and long, and it becomes increasingly important for students to know and use multiple strategies and think about which problem-solving strategies might be most appropriate. Arguably, this might be more important in secondary school than it is in elementary school. So in the time that I have left, I'd like to speak a bit about what teachers can do to promote flexibility in their classrooms. I'm going to talk to you about several ways that I think teachers can promote flexibility in their classrooms. First, teachers can incorporate multiple strategies into their teaching. All math problems can be solved in more than one way. Students may be conditioned to think that any strategy they use is fine as long as it produces the right answer, and that they will get a good grade if they use the one method that their teacher used. But teachers should be open to and even ask students to produce more than one way to solve problems. In some math topics, we are already doing this. For example, I think of the multiple ways that we teach for solving systems of linear equations, or the solving of quadratic equations, or the graphing of linear functions. But I'd like to see this focus on multiple strategies present in all of our math teaching. Second, teachers can compare and contrast these multiple strategies. My colleagues and I have done a series of studies exploring the power of comparison in students' mathematics learning. Psychologically speaking, we know that comparison plays an important role in learning of math as well as other subjects. Yet when teachers and students are engaging with multiple strategies, there's a lot of information that needs to be processed. Some teachers say to us, my students have a hard enough time learning one strategy, and yet you are asking me to teach them multiple strategies. The possibility of overload is real. But we've learned that there is an instructional approach that allows teachers to engage in multiple strategies without overloading their students. I don't have time today to go into this approach in depth, but it involves a particular way of presenting the to-be-compared multiple strategies, some careful thinking about when the best time is to engage students in comparing multiple strategies, and consideration of how teachers can use visual aids and gestures to support students thinking about multiple strategies. Getting students to engage successfully with the learning of multiple strategies not only requires a change to the content, but it also involves some changes to teachers' pedagogy. And this leads me to talk about mathematical discussions. Flexibility can be promoted when students engage in certain kinds of mathematical discussions in the classroom, namely discussions about the affordances and constraints of the multiple strategies that they are learning. When a particular strategy is applicable, this is something that students should be attending to and discussing. When is a strategy applicable or useful for solving a problem? What mathematical or structural features need to be present in a problem for a given strategy to apply? And how does the strategy take advantage of these features when implemented? What makes one strategy better than another? Is it more efficient, less likely to lead to error, more innovative, more elegant? In these discussions, the teacher becomes someone who is asking a lot of questions and orchestrating the ensuing conversation. Doing so can turn students' attention from merely a focus on their answers to a consideration of the process of problem solving. And this is where the deep conceptual and procedural knowledge development can occur. Engaging in these kinds of discussions may be new for many teachers who are used to lecturing in the front of the classroom for most of the lesson. And so teachers will need professional development and support in learning how to engage students in discussions. But doing so is essential for the development of flexibility. I think I'm reaching the time where I need to conclude. And so to close, let me give you the briefest answers to what I've spoken about with regard to the three questions that were the focus of this talk. First, I wanted to talk to you about what is mathematical flexibility. And you can think of flexibility as knowledge of multiple strategies and the ability to select the most appropriate strategy for a given problem. Second, I was interested in talking about why flexibility would be an important learning outcome from students, especially at the secondary level. And I noted that flexibility is linked to improved performance in mathematics and also represents a core disciplinary component of what it means to know and do mathematics. And third, what teaching practices help promote flexibility? I talked about several, including exposing students to multiple strategies, using comparison to help students avoid overload, and engaging students in mathematical discussions about the strategies that they are learning. I'm going to stop there. Thank you so much for your attention. I'm glad to be in conversation with you about flexibility. Please email me if I can be helpful to you.